This topic is about crude oil and fuels, so it's probably useful to know what crude oil is. Crude oil is made from ancient biomass found in rocks, so things like the remains of dead plants and animals from thousands, possibly even millions of years ago. And it's a mixture of lots of different chemicals. So if we can separate out those chemicals, we can get lots of useful materials like fuels. The way that we separate it out is by doing something called fractional distillation. And then some of these fractions, some of the chemicals that are separated out, can then be used as fuels. This topic also looks at something called biofuels. So that's kind of making fuels from plant material, more kind of natural things than perhaps your ancient biomass could be considered to be. You've got to think about whether fuels that we're looking at are renewable, so we can make lots more, or non-renewable. Either we can't make more, or it would take thousands and thousands of years, in which case we say there's a finite amount of them, a limited amount of them. You've got to evaluate the impact on the environment of burning hydrocarbon fuels, and we'll look at combustion, burning, and the reactions of hydrocarbon fuels, so fuels with hydrogen and carbon in them. And you also need to think, just like your quarrying, just like your mining, what are the social, economic and environmental impacts of using different fuels? You might be given data about other fuels to the ones that we're studying here in the exam. Don't panic if you see this, just look at the information and state the information, the evidence in your answer to your question. You also might need to evaluate developments in the field of producing better fuels, things like ethanol and hydrogen. So you do need to think about these as renewable resources, and especially for the hydrogen, you want to think about the storage and the use of those fuels. Hydrogen is highly explosive, so you do need to be careful how you store it and how you use it. It might be a bit tricky still to use that in a vehicle, perhaps. Boom! And you also need to think about the products of combustion. So if you burn hydrogen, you only actually get water. If you burn or you combust other things, though, you often get carbon dioxide, which is a greenhouse gas. You've also got to think about evaluating the benefits, drawbacks and risks of using plant materials to produce fuels, which we'll look at in a moment. So we said that crude oil is a mixture. It's a mixture of lots of different compounds. And a mixture is anything where you've got two or more elements or compounds not chemically combined together. So that means each substance, each chemical in the mixture still has the same properties, and you should be able to separate out those substances using something like distillation. Distillation is where you heat something up so it evaporates and then cool it down again so it condenses. So evaporation, liquid to gas, followed by condensation, gas to liquid. Just be careful with these definitions of what elements, compounds and mixtures are. Element is just one type of atom, so here we've got element X, element Y for example. A mixture would be where these things are mixed together, but a compound is where they are actually bonded together, they are joined chemically together. A mixture, they're not joined chemically together, and that's why we're able to separate them out. A lot of these chemicals in our crude oil are made of hydrocarbons, so these are molecules, these are chemicals that only have hydrogen and carbon atoms in them. And most of these hydrocarbons, most of these chemicals are known as something called alkanes, and they have the general formula CnH2n plus 2. So however many carbon atoms you've got twice as many plus 2 hydrogen atoms. Let's look at a couple of examples for this. So we've got methane, ethane, propane and butane. It carries on and you get pentane as in a pentagon with 5 sides, but the main ones you need to know are methane, ethane, propane and butane. We said CnH2n plus 2. So for every carbon atom, you times that by 2 and add 2 more to it to find out our hydrogens. So in methane, 1 carbon, 1 times 2 is 2, adding the extra 2 on is 4, and check 1, 2, 3, 4 hydrogens. Each carbon can form 4 bonds, and each hydrogen can only form 1 bond. Check again for your ethane. If you have 2 carbons, 2 times 2 is 4, add another 2 is 6, so 1, 2, 3, 4, 5, 6 hydrogens, CnH2n plus 2. In your propane, Your number of carbons, your N, is 3. So 2 times 3 is 6, plus another 2 is 8. And you can see you've got 8 hydrogens. Butane, your N is 4, so 4 carbons. 2 times 4 is 8, plus another 2 is 10. And you've got 10 hydrogens around your carbons in butane. Every time, look and see, you can see that every time the carbon has 1, 2, 3, 4 bonds around it. Sometimes that's a bond to hydrogen, sometimes that's a bond to another carbon, but each hydrogen will only ever have one. Make sure you can draw the examples for methane, ethane, propane and butane. So as well as being able to draw out the alkane molecules, you need to be able to write them as well. In order to write them, count up how many carbons you've got, and that gives you this number here, C2 in this example. Then count up how many hydrogens you've got, and that gives you this number here, 6. So looking again at our examples, your different formulas would be CH4 for methane, C2H6 for ethane, C3H8 for propane, and C4H10 for butane. The process that we mentioned for how we split up these hydrocarbons, these different chemicals in crude oil, into the separate ones that we can use, which we sometimes refer to as fractions, these separate chemicals, is a process known as fractional distillation. And what happens is the molecules that have a similar number of carbons will actually evaporate and condense at a similar temperature. So if you evaporate your crude oil and then let it cool down and condense, so evaporate, go from a liquid to a gas, condense, go from a gas to a liquid again. And if you do that at a lot of different temperatures, then you'll be able to separate out the fractions, separate out those groups of molecules with similar numbers of carbons. You need to know how this happens because it's often a question in the exam where it'll ask you what is fractional distillation or how does fractional distillation work. Specification refers to something called a fractionating column, and that would be a diagram that looks something like this. Your crude oil is put into a furnace, so furnace is in heating it up, making it hotter, and so that's going to evaporate your crude oil, it's going to turn it into a gas. Then when it's inside the fractionating column, this kind of machine here, there's going to be different temperatures, so it's much cooler at the top, only 20 degrees Celsius, and much hotter at the bottom, 400 degrees Celsius. Different chemicals are going to condense, because remember you've heated them up, you've turned them into a gas, they're going to condense and go back from a gas to a liquid at different temperatures. So for example, things like petroleum gas will condense at a much lower temperature, around 20 degrees Celsius, and you can separate that off. If you have your kerosene or your diesel or your industrial fuel oil, then they're going to condense, go from a gas to a liquid at much higher temperatures. And the difference in temperatures in the fractionating column allows you to separate out the different fractions, the different chemicals. The different chemicals have different properties depending on what size they are. So the ones that are up at the top of the fractionating column are much smaller, and the ones at the bottom are much, much larger. So these ones here are much bigger molecules. The size will affect how they are used as fuels, because the size will affect their boiling point, their viscosity, so how thick they are or how runny they are. And it will also affect their flammability, so how easily they set on fire. In terms of the boiling points, if it's smaller, it's going to have a much lower boiling point. In terms of the viscosity, if it is smaller, it's going to be much runnier. We say it's not very viscous. If it's a bigger molecule, we'll say it has high viscosity, so it'll be quite sticky, almost something like syrup in terms of its texture. And the flammability, the smaller they are, the more flammable they are, the more likely they are to set on fire. So the small ones at the top have low boiling points, low viscosity, and high flammability, whereas the larger molecules at the bottom have higher boiling points, higher viscosity, and lower flammability. You need to know about how our hydrocarbon fuels might lead to pollution. So you do need to know about combustion. Combustion is just another word for burning. So when you burn a fuel, if it is complete combustion, so it's completely burnt in oxygen, then you make carbon dioxide. If it is incomplete or partial combustion, then there won't be very much oxygen there, and actually you're going to end up with carbon monoxide instead, so CO, instead of the CO2 that you would make if there was lots of oxygen there. You don't need to know how oxides of nitrogen, so nitrogen oxides, are made, other than the fact that they're just formed at high temperatures. So the nitrogen in the air around us will react at high temperatures, and that's how we get nitrogen oxides. The other things that can be made from combustion are things like water vapour, and you also get sulfur dioxide because some fuels might contain sulfur, which will react with the oxygen when it's burning. And we also mentioned oxides of nitrogen as well, which are formed at high temperatures. Solid particles, which are sometimes called particulates, might also be released, and these solid particles might contain soot, which would be carbon. So if you had incomplete combustion, partial combustion, you might make carbon monoxide, but you also might just make some carbon by itself. And if any of the fuel is unburnt, if it doesn't combust, that would also be solid particles. When we combust our fuels, when we burn them, that releases energy. And we say that during combustion, the carbon and the hydrogen in our hydrocarbon are oxidized. So carbon is oxidized to make carbon dioxide, hydrogen is oxidized to make water, H2O. Some of the other products of combustion can cause environmental problems. So the sulfur dioxide that we mentioned can be made because of the sulfur in the fuels, and the oxides of nitrogen can both cause acid rain. The carbon dioxide can cause global warming, and those solid particles, things like the unburnt hydrocarbons and the carbon that might be made in partial combustion, can cause something called global dimming. The particles get in the way of the light and we can't see the sunlight quite so much. So because of that, we're trying to do things like removing sulfur from fuels before they're burnt. So in vehicles, we try and make sure that we don't have any sulfur in the fuel so it doesn't get burnt, it doesn't make that sulfur dioxide, it doesn't make the acid rain. In power stations, once the combustion has already happened, that sulfur dioxide can actually be removed from the waste gases so that it doesn't go out into the atmosphere. You also need to know about biofuels and how they can be used. So biofuels are things like biodiesel and ethanol. You look at ethanol in a bit more detail in one of the later topics in core, but essentially at the moment what you need to know is these fuels are made from plant materials rather than fossil fuels, and there are some issues surrounding their use, mostly economic, to do with money, ethical, to do with whether we think it's right or not, and environmental issues. One of the key issues with biofuels is that people have said that if we're growing crops to use for biofuels, then that's limiting the amount of crops that are grown for food, and in some countries that is causing a problem. The reactions of hydrocarbons can be summed up in this diagram here. So we take our hydrocarbon fuels, so our fuels that are made up of hydrogen and carbon that sometimes have a bit of sulfur in them. We need these hydrocarbon fuels for transport and also for electricity production and for heating our homes. And what happens when we burn them, when they're combusted, is that the carbon and the hydrogen are oxidized. They turn into carbon dioxide and water if it is complete combustion. If it's incomplete combustion, then we actually just get CO, carbon monoxide, instead of carbon dioxide, or we might just get C, that carbon. So some of the things that are produced when we burn are, as we said, the particulates, things like carbon, and that can lead to global dimming. Things like sulfur dioxide that are made from the sulfur burning in oxygen, and nitrogen oxides, they can lead to acid rain. You could be asked about any of these things here, and don't forget that your carbon dioxide can lead to global warming. So we do need hydrocarbon fuels for transport, for electricity, for heating, but don't forget that they have problems associated with them, or rather they have problems associated with the products of combustion.